Hey there everyone, and welcome to the third and final video covering material that we need to cover while I'm gone. In this video we'll talk about what it means to take a complex derivative, essentially, and then we'll be almost done with the calculus of complex functions. We're saving integration for the next subunit. So this differentiation video finishes off mostly. There'll be a little bit of stuff left when we get back in class, but mostly finishes off the differentiability part of complex functions. So two goals in this video. First, talk about what is the derivative of a complex function, and then given a complex function, how can we tell if it has a derivative or not? And this turns out to be a much more complicated question than what you saw in Calc 1 conceptually. Now, in practice, there's a way to easily tell, but this now is finally sort of much different than you might expect from Calculus 1. So what is the derivative of a complex function? Hopefully this looks very familiar to you. This is the definition of derivative exactly as you saw it in Calculus 1, except this is a complex number here. So as h approaches 0, the complex number, and z can be a complex number, and z is a complex number. But this is exactly what you would write down if all you remembered was the Calculus 1 definition and you had to make a guess what the complex definition would be. This is the only sensible thing to write down. And there it is. And so, given this definition, everything you know and love from Calculus 1 basically still holds of the differentiation rules. So like the power rule still holds. The derivative of a sum, you can still split it over the sum, like this. The chain rule still holds. The product rule still holds. The quotient rule still holds. The derivative of complex log is 1 over z. We knew that from Calc 1. The derivative of complex exponential function with a constant here, you just drop the constant down and then copy and paste, where c here is any constant complex number. So c doesn't have to be a 5, it could be a 5 plus 10i or something, but it just pops down. So basically, once you put this derivative definition in place, a lot of the stuff that you remember from Calc 1 in terms of rules just comes right along. So that's nice. So let's think about finding the derivative of a function at a particular number for this function, z squared plus I. And let's think about f prime of 4 minus 2i. So the definition from the previous slide makes us write down this. F of 4 minus 2i plus h minus f of quantity 4 minus 2i all over h. And the basic idea here is that 4 minus 2i plus h, if h is really small, and it's going to be small since you're letting it go to 0 basically, what you're doing is you're looking at points, 4 minus 2h, you're looking at points close to 4 minus 2i, so like around here. And then you're comparing the outputs of those to just the output at 4 minus 2i and dividing by h, which is exactly what you did in Calc 1. And in Calc 1, you got slopes of secant lines when you did that. This is the limit of slopes of secant lines giving you the slope of the tangent line in Calc 1. Here it's a little different because we don't have tangent lines per se. At least we haven't defined that because complex functions are different. Input 2 dimensions, output 2 dimensions means tangent lines aren't quite as natural as they were in Calculus 1. But anyway, let's think about what this derivative should be with this limit definition. Just like Calculus 1, by the way, you don't usually wrestle with the limit definition that much because there are rules like all of these to get around it. But let's at least see one or two computations where you wrestle with the actual definition. Okay, so here f prime by definition is f of this thing minus f of this thing. Remember, f itself was z squared plus I. So here's z squared, where you're inputting 4 minus 2i plus h squared plus I minus, again, z squared plus I, but the input z this time is 4 minus 2i. If you expand out that numerator, you get this, and then you can cancel h there, h there, h there. And when you substitute in 0 plus 0i for h, you're left with 8 minus 4i. And there you go. The derivative of z squared plus I at 4 minus 2i is 8 minus 4i. And notice you get the same thing if you were like, well, if I just took a derivative like I'm in Calc 1, so if I come back here, I mean, I is just a constant. Don't I just do 2z and then derivative of constant is 0, right? Constant still should have no rate of change, right? And yeah, so that still works. So f prime of z is just 2z. So if you just plug 4 minus 2i into that, you get 8 minus 4i, just like we got. So it all works out the way you think it should, whether you use the definition or whether you use all these formulas that I kind of glibly wrote down. Now you do have to prove these from the definition, right? So it's not like these formulas exist independent of this definition, but whatever. It all works out the way you think it should. Okay, so just a bit of vocabulary. Missing my y here. Bit of vocabulary. A function f is complex differentiable if basically its derivative exists for every point in the domain. So that's the same definition of differentiable we had in Calculus 1. A function is differentiable if its derivative exists at every domain point. In complex world, there's actually multiple ways of expressing differentiability. So complex differentiable is one way, analytic is another. The fanciest word is holomorphic. So depending on how fancy you want to sound, you can say holomorphic in our class, or you can say analytic. I say analytic myself most of the time. Okay, so now that we have the idea of a complex derivative, let's think about this. What kind of complex functions are analytic? What kind of complex functions have a derivative? And in Calculus 1, almost anything we wrote down had a derivative, like sine, cosine, e to the 8x, sine of e to the 8x, whatever. You had to kind of work pretty hard to write down a function that wasn't differentiable. You had to go to piecewise functions, or like the absolute value function, which is piecewise, right? You had to work. You had to work to get functions not to be differentiable, because you had to introduce sharpness into the graph somehow. Right? That's one classic way to break differentiability, is to have a sharp point instead of something smooth. Anyway, so complex functions. What kind of functions have derivatives? So now things are going to get way different than Calc 1, because here's a function that is sort of as tame as you can imagine. You input x plus yi, and it outputs an x. So you input 2 plus 3i, it outputs a 2. Just reads off the real part. So again, if we were in class, I would be scanning your faces to make sure that you agree with me that this is about as tame of a function as you can write down. There's nothing wacky there, nothing crazy here. I'm not putting something piecewise here, or like doing, sine of log of absolute value or something. Nothing crazy. This is like pretty tame. And it was easy to write down. So shouldn't this function have a derivative? Is this function analytic? And surprisingly, the answer is no. It turns out that it's like as non-differentiable as you can imagine. F prime of z naught doesn't exist for any complex number. So it's like nowhere differentiable. There's not a single complex number at which the derivative makes sense for this function. And again, I just want you to, before I justify this to you, I want you to process that this cute little function here that looks as tame as you can possibly get, it just looks like a linear function, doesn't it? Isn't x just a linear thing? Why isn't the derivative just 1 or something, right? But anyway, notice if this were like f of z equaled z, which is not the real part of z, right? If f of z equaled z, the derivative would be 1. But this is different. This is input a complex number a plus bi, and you read off the a. Anyway, so this function is nowhere differentiable. There is not a single complex number at which this function has a derivative. So let me justify that to you real quick, because it really should be shocking to you that this function has no derivative. So I'm just going to pick a number in the complex plane that's nice. The same logic works for any complex number. I'm going to explain to you why the derivative of this function does not exist at 1 plus I. So if you think back to the previous picture, like with this, so as h goes to 0, again, we're just picking like points in the neighborhood of 4 minus 2i and then walking towards 4 minus 2i. So you could do that from the north, you could do it from the south, east, west, whatever. You could do like a northwest kind of approach. Same kind of thing as the limits in the previous video. It's just as h is getting close to 0, you're just approaching 4 minus 2i and then taking an output. And you can approach 4 minus 2i from many, many different directions. So here, I'm going to approach 4 minus 2i along a horizontal line, so like an east-west kind of deal, using numbers that look like this. And so notice, if I take 1 plus I, 1 plus I, and I fiddle with the real part like this, I'm keeping my complex numbers at the same height. So let me go back to my picture of the complex plane. So 1 plus I is right here. 2 plus I is here. 3 plus I is here. So if you fiddle with the real part, you're keeping things at the same height. If you fiddle only with the imaginary part, you're keeping things along the same vertical line. So here's 1 plus I, 1 plus 2i, 1 plus 3i, and so on at the same vertical line. So that's all I'm saying here. Like, if I look at numbers that look like this, where h is small, I'm just looking at numbers that are close to 1 plus I, but left or right. And if I look at numbers that look like this, if h is small, then again, I'm looking at numbers that are close to 1 plus I, but you're going north-south. And here I'm slightly abusing notation. Here I am assuming h is a real number, but it doesn't matter. Let's slough over that detail. Okay, so let's think about f prime of 1 plus I approaching left to right. So this is like an east-west approach to 1 plus I. If you just process what's happening here, so the real part of 1 plus h plus I is just 1 plus h. The real part of 1 plus I is 1. And then you subtract. So you end up with h over h. So this limit is 1. But if you approach 1 plus I up, down, north, south by fiddling with the imaginary part, like this, so now the real part of all this is just 1, because the h is now attached to the I. The real part of this is still 1. 1 minus 1 is 0. Like, there's no more h in the real part. So all of that to say, the punchline of this is, if you're trying to take the derivative of 1 plus I, and you're walking towards 1 plus I, if you walk towards 1 plus I along an east-west axis, a horizontal line, then your derivative is supposed to be 1. But if you walk towards 1 plus I along a north-south axis, your derivative is supposed to be 0. But it can't be both. Your derivative can't be both 1 and 0. Therefore, the derivative doesn't exist. So the punchline here is that this is about as friendly a function as you can imagine. And sorry, it's supposed to be a y here. So this is about as friendly a function as you can imagine, but it has no derivative, actually. So it's kind of nuts, right? Anyway, that's a pretty cute example. Okay, so if I give you a complex function in a sort of standard form from a previous video, right, like a real part and an imaginary part, if I give you a function in this form, is there an easy way to tell if it has a derivative or not? Because here, like, did I have to actually cook this up? Like, oh, okay, I gotta pick a number and then think about different ways of approaching that number. Do I have to do that every time? And the answer is no. It turns out there's a really quick check whether a function is analytic or not. Now, of course, proving this is much different. I'm just giving you the result. So what I'm about to show you, I'm not claiming it's obvious or something, but there is a very easy check to tell if a complex function has a derivative, and it's called the Cauchy-Riemann equations. So a complex function written in this form, so real stuff plus imaginary stuff, that thing has a derivative if and only if the x partial of u equals the y partial of v, and the x partial of v equals the negative y partial of u. Okay, this is the Cauchy-Riemann equations. If these two equations are satisfied, your original function has a derivative. If one of those two is not satisfied, your original function does not have a derivative. And again, if we were in class, I'd be looking at your faces, looking for the shock on your face. Because if you think about it, these are really stringent, these conditions. Really stringent. If you just write down a random, like, function here, random function here, even if they're friendly, x cubed, sine x, sine y, whatever, you're not going to just stumble into these equations on accident. Most choices of functions you put here are not going to satisfy these things. So It's very difficult, actually, in some sense, for a complex function to have a derivative in a way that it wasn't difficult in Calc 1. In Calc 1, like, everything had a derivative unless you tried to make it not. Now it's kind of the opposite. You have to kind of try to come up with functions that have derivatives if you have it written in this form. And then finally, this theorem also tells you, like, if you know the function has a derivative, then the derivative just, here's a formula for it. The derivative of f, assuming it exists, is the x partial of u plus I times the x partial of v, which, if these equations are satisfied, ux and vy are the same thing. So see vy and ux, and vx and negative uy are the same thing. So I can just replace. So if these Cauchy-Riemann equations are satisfied, you can tell me what the derivative is starting from this form of the function. Now, of course, if your function is written, sorry to do this, go all the way back. If your function is written like z cubed, then you know the answer is 3z squared. If your function is e to the 5z, the answer is 5e to the 5z, whatever, right? But these functions like this, notice, are not written in sort of standard form as like real thing plus imaginary thing. Like this function here is written in the standard form. X plus 0i is how you would read this. So this function f has a real part x and an imaginary part 0. You know. Okay. So here are a couple of things for you to try. So I would pause the video here if I were you and try this, but you can use these equations to show that this function is analytic, as it should be, because f prime of z is supposed to be 2z if things are working properly, right? But what I want you to do is I want you to write this function in this form. So instead of a z, put an x plus yi. I want you to square the x plus yi and break things down like this, and then check that the Cauchy-Riemann equations hold, and then write the derivative down in this form. And then you can check if that equals 2z or not. I sure hope it does. And then this function here I've written in the u plus vi form. And this function, again, looks awfully friendly to me. It's just kind of like a quadratic looking thing. The question is, does this have a derivative? So here's u. So u sub x is 2x. Here's v. Right, you ignore the I. Here's v. v is y squared. Y squared. V sub y is 2y, you know. Okay, so explain that this is analytic by writing it in standard form, checking these equations, and then write down its derivative in this form. And then explain why this is analytic or not by checking these Cauchy-Riemann equations. So when I get back, I'm going to first ask you what you thought about all of this. Was this understandable? Do you need more examples, etc.? There's a slight bit more derivative material that we need to cover before we're sort of done with the complex derivative stuff, before we move on to integration. So we will cover that when I'll get back. But I mainly just want to make sure that everybody is on board with what I've shown you here. So the main upshot of this material is taking derivatives of complex things is a bit different than real things, especially if you're going to write your complex function in this form. If you write your complex function in this form, it's actually pretty hard for a function to have a derivative, which is very strange. So the punchline really here is the Cauchy-Riemann equations. If your function is written like this, f of z equals z cubed or something, then you just know the derivative is 3z squared. It's fine. But some functions are handed to you like this. Like the functions tell you what they do to the real part, what they do to the imaginary part, you know. And the Cauchy-Riemann equations tell you how to handle functions like that if you want to know their derivatives. So this really is the punchline of this video. We understand now what a complex derivative is, and generally speaking, we can find them if they exist, and if they don't exist, we can say why, because we know about these equations.